particular, I want to discuss some things related to the basic space. At the beginning of algebraic geometry. There's projective space. My notation is P of E. Or if you take a basis, Pn of V and C in a basis. Let me review what that means. Particularly VI is here new, so let me sketch just what we have. We have, say, basis. I choose intentionally n plus 1 dimensional space. The vector space of E. And every vector in this vector space can be written in coordinates. Let's even emphasize that. And in fact, let's emphasize the fact that these zi's are linear functionals on space. And so we have a mapping which sends a vector to its coordinates. Of course, an isomorphism from V to Cn. And it sends the line spanned by this vector, so it's not zero, to the, what we call homogeneous coordinates. And this means that this vector is, this homogeneous coordinates is the equivalence class of this vector modulo dilation. So the vector modulo dilation, okay, scalar multiplication. So it doesn't matter which vector you take in this line, you get the same equivalence class. And so the projective space, which is the set of one-dimensional subspaces, so we often say that a set of lines, but we really mean subspace, can be really thought of as just being parameterized by these homogeneous coordinates. So the charts on this projective space are U, say L, and that's the set of vectors such that ZL of the vector is not zero, and just as some L walks in here. I have just been dedicating this to you, to be precise here. I often write that. So that's an open set. And if you're in this set, so if we are in this set, so a line in this set, which is homogeneous coordinates in this set, set UL is mapped by the coordinate map by division by ZL. Of course, I leave this one out, so let me write here L minus 1 and L minus 2, L plus 1. I leave the middle one out. This is the coordinate in Cn This is a coordinate mapping. Maybe we call this phi L, and this identifies UL with Cn is a very big chart. Very, very big. The complement of it is where ZL is equal to 0, and it's a very small set. And it's defined by the equation ZL equals 0, which is an algebraic equation. So the complement is closed in the algebraic sense. The algebraic closed sets are defined by polynomials of rational functions. Now I hear a question someplace.
How do you cover 0? How do you cover 0?
What do you mean how I cover 0?
0 doesn't seem in any of the ELs.
Yeah, because that's important that 0 is not there, because we're discussing the space of lines. I mean, maybe, let me see, what do you mean? Say it again, please. How?
So 0 is not in the projective space, huh?
No, a point in projective space is a one-dimensional subspace.
Yeah.
And, yeah, you see,
So
so
V in the beginning should be non-zero.
that's right. If we take V equal to 0, we're in trouble. We have to take it to generate the line.
Okay.
That's the point. That's the reason your question is good. So it generates the line, and then we get these coordinates. So you can check that the coordinate change of coordinates say from UI J, if you like, to UJI, these are the intersections of these two sets, maybe we call this PIJ. It's simply, if you look at it, what it really is, it's probably ZI over ZJ, I think. You have to check whether it's ZI over ZJ or ZJ over ZI. It's this rational change of coordinates. So everything here is algebraic, and this is indeed an algebraic structure on the space. Okay, that's projective space. So the special case that you've seen already, of course, is the Riemann sphere. And so P1C, so this is the projective space of C2. And the point here, we've used notation. A point here has coordinates, homogeneous coordinates, Z0, Z1. And we have two sets, U0 and I'll write them out long, so U0 is where Z0 is not equal to 0. And U1 is where Z1 is not equal to 0.
Zero there.
0. Thank you. And if we take a homogeneous coordinate here, so here Z0 is not equal to 0, so we can normalize this coordinate, Z0, and call it 1. Okay, if you want, I'll write here Z0 over Z1, and the coordinate map takes that to, Z1 over Z0 takes it to that. So that's the coordinate there. And maybe we call this Z. And here, if we have take one here, then we know Z1 is not equal to 0, so we can divide by that, so that we can go to Z1, Z0 over Z1. And maybe we call this coordinate zeta. And the change of coordinates, obviously, how do you go from Z to zeta? So zeta, if you visualize on the intersection as a function of Z, which, as you see, is 1 over Z. So this is well known to you, I think. So it has the big open set. Let's say the North Pole is where Z0 is 0. No, I prefer maybe where, I don't know, it doesn't matter. Where Z0 is 0. Let's call this 0. And the South Pole is maybe where Z1 is 0. And we call this infinity. And so, actually, to be consistent with complex analysis in one variable probably I will call this infinity. And this 0. Let me make sure. Yes. Because this variable is used for the usual coordinate on complex plane. And where this variable is 0 is here, 1, 0. So this is the complex plane. We have got this thing set up is this one. It's where, yes, so the complex plane is usually the z plane, which I guess is where is u0. Right. And the origin in u0 is this one. And infinity is that. So you've done this all your life in complex analysis in one variable. Okay, so that's a global thing, and I would like now to talk about meromorphic functions on these global things. These manifolds. In general, so if X is a complex manifold, that means a real manifold where the charts have values in Cn and the change of variables is holomorphic. Then a meromorphic function, and we'll use the notation M of X. It's a space of meromorphic functions. Let's just for fun here take it to be connected, which makes life a little bit on the formal base easier, because then this is a field, and this is called the function field of the manifold. You see, if it's not connected, you have divisors of 0. You could have 0 on this component, 1 on this component, and it's crazy. So take it to be connected, and then it's really a field. So we call this the function field of the manifold X. Let's recall what the definition is. So what is M? M means this. There is a covering by open sets, of course, U alpha of X. And on each U alpha, you have meromorphic functions, but of a special form, namely a quotient of two holomorphic functions. O of U alpha is my notation for this ring of holomorphic functions. By the way, notation was introduced by Serre, and the reason it's called O, you will enjoy this, is because H does not exist in French, and when you speak in French, you say holomorphie, and so he called it O. I don't know if it's a true story, but I think it's a nice story. So anyway, these are the holomorphic functions. And now here in this case, where this is a manifold, we can choose.
M alphas are restrictions, or
What?
M alphas are restrictions, or
What about restriction?
M alpha is a restriction, or what is it?
No, M alpha is a function on U alpha.
Okay.
Okay? If you like, M alpha is a pair of functions on U alpha.
Okay.
Okay? And now I'm going to define M. So I haven't finished the definition yet.
Okay.
So you may think, of course, that M alpha is for sure the restriction, but M is defined by M alpha. Okay. Okay, and you may choose. We may choose. The M alpha to be relatively prime. The F alpha, choose F alpha and G alpha to be relatively prime. And in fact, you can choose this to be relatively prime everywhere on U alpha. So let me just comment on this. This may look like a mysterious thing to you. Let me demysterious, make it, I don't know what the word is, make it less mysterious. Recall in one complex variable for this statement. without loss of generality in dimension 1, we may choose these two functions, so I can localize and take them smaller, f alpha either, well, let's say they choose f alpha and g alpha, so that either f alpha is nowhere 0, or g alpha is nowhere 0. On u alpha. This is completely clear because this definition is local and I can make it smaller and smaller. So okay. So and then if they both happen to have 0 at this point of consideration where I'm taking them smaller, I cancel. This is the key thing. At that point, locally, it's a unique factorization domain. You can cancel. You can really cancel. You know, factor out and cancel. And the local rings here, so you see what I did here. I localize, 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 and cancel. The same thing here, you can localize at one point, and in fact you can say the same thing as here, but you can't, you can say this thing. You see, this is the statement everywhere, at every point, what do you call it? I want to say, somebody speak German here, Teilefremd. You're German. What is Teilefremd in English?
Relatively prime.
Yeah, relatively prime. So at each point in each local ring when you're looking at the functions, here it was a joke. We just take these things small enough so either one vanishes or the other does not vanish. You see, this is a joke. But in several values you cannot do this because you see what happens is you have the situation of the 0 set of F and the 0 set of G. Here maybe the point of interest you want to, it might be something like this. You can never ensure that they are both not 0 at the same point. It's just impossible. What you can ensure is that they don't have any components which agree with each other. Because of their components which agree with each other, you can cancel them. That's no proof, but that's the way you deal with these matters in this local ring. Okay, you have to discuss irreducibility and so on, and it's somewhat painful first remark in the local theory. So all I'm just saying here, you can always choose these things to be locally Teilefremd, relatively prime. Okay, that's the best you can do. Okay, and this is what Mihai is saying. What you're saying, what you expect here is, so the condition here is, well, let me just write it, is F alpha G beta equals F beta G alpha, or minus equals 0 on the intersection of these open sets. That's the condition of compatibility. If you, well, you want to write it in the ring, you don't want to write it in the field here, you want to write this in the ring. And so this, but in the way you're thinking, and then say the restriction of M alpha to U alpha beta and M beta to U alpha beta is equal. So it's compatible and globalizes in that sense, but only locally it is a quotient. Okay. That's the definition of a meromorphic function. It is a field and so on. What?
So where is M in this definition?
Okay, M, if you like, thank you. M, if you like, is an equivalence class of coverings and local representations in this form. That's a very good question you're asking. what I wrote down for you on the blackboard is a representative of a meromorphic function. And now if you take another covering and another, say, U alpha hat, M alpha hat, you have to say what it means that these two things are equivalent. What it means, obviously, is you take a refinement of the two coverings and then take restriction maps and everything agrees.
Okay. Did you explain in the previous lecture how this fits with the definition of finitely many points where it vanishes in one dimension?
I just explained it here. Well, I explained it here, not finitely, but discretely many.
Discretely many.
Yeah, because I just pointed out here, you can always localize so that either one or the other is not zero. That's what I just said here. Okay. So the identity principle is, of course, used here. Okay. Okay. So that's the notion of a meromorphic function field. And I hope today I can give some examples. The first new idea, perhaps, I think is fundamental. I don't know where is Romania here? Oh, there it is. Is this 1871. Yes. By the way, when I first came to Germany, you're German, I think. We had dinner with some members of the old German military. And he pulled out such a map and explained to me where the definition of Germany, how it should be. And that definition is also on this map, if you want to take a look at it. For example, you notice, for example, the Danzig, Königsberg. Maybe you know Königsberg. There's some very famous mathematicians in Königsberg. You know some of them, right? Well, I think maybe Hilbert.
Yeah,
Kant was also from Königsberg, perhaps. Huh?
Euler, the same bridges of...
Yes, but Euler, he went to the Schweiz to make money, like everybody. Then he left to go to Berlin. He got in a fight with somebody, was it, I don't know, Friedrich Golson, one of somebody like this, and got mad for some reason, and then went to Leningrad, naturally, St. Petersburg.
But the famous for the 5 or 7 bridges of Königsberg with Euler.
Right. But it was already, but he was a big shot, you know. I mean, he had 20 assistants and so on. So that's not enough for me. We only had 5 or 6. I don't even know what the idea was I was going to talk about. I got distracted by this. I got distracted by this map. Okay, an idea which I think is a fundamental idea, and I don't know how to contribute this idea to somebody, is in dimension 1, that a meromorphic function is a map, is a holomorphic map let me call it by the same letter, M from X to P1. It's a holomorphic map. And now I'm going to be a little bit careful with the notation. I'm going to put a half arrow here because there's some very interesting things that happen in higher dimensions. But let's first talk about it in dimension 1. Okay? We're just intuitively in dimension 1. So watch this. On U alpha, so if this thing is given to you on U alpha, this guy, at least in your head, is F alpha divided by G alpha with these two things relatively prime at every point of consideration. So, I mean, after all, what that means is that we're looking at these things homogeneously. All right? That's what it means. In that first coordinate chart, that's really what that means. Yeah? And you see in dimension 1, either this is non-zero or this is non-zero. We can localize that situation. So that means that this map is well defined in dimension 1. This is Mihai's point before. He was worried about where is 0 here. If both of these things are 0, for example, in my little picture here, at this point here, there's some trouble. We call that a point of indeterminacy, and I want to really talk about that. But let's think about it in dimension 1. At least this is well defined. And of course, holomorphic, you just check it. Most places, so let me emphasize, as long as either F alpha or G alpha is not 0. Because one or the other is not 0. So you see, that means in most places it's okay. It's only bad where both their 0 sets intersect. Let me just state for your benefit, in higher dimensions, where this problem really happens, difficulties really happen. In one dimension they don't happen, so in higher dimension where difficulties really occur. Let me just mention F equals 0, intersect G equals 0. You will notice that these sets are well defined, where these sets of 0 are well defined. So where that happens is two codimensional. I mean, really, you should think whatever the devil that means. If they're smooth and transversal, it means it's a two codimensional complex manifold. You can think over the real numbers. This is 4 real codimensional, so it's very small. In this case, where I drew some pictures of singularities, measure theoretically, and everything in every regard, these intersection points have size codimension 2, complex codimension 2, or real codimension 4. Okay, so this is only a small set, but an interesting set. Okay, where these things could be 0. So let's look at the, let's not look at that right now, let's just look at the one-dimensional case. By the way, let me call this set here I of n for fun, and you call it the indeterminacy set of this mapping n. It means you don't know what the value is. It's not infinity, it's not 0, you don't know what to say. So it's indeterminate. So this indeterminacy set is two codimensional. So let's look at the one-dimensional case where everything's okay. So the meromorphic functions on such a thing is simply the holomorphic maps from X to P1. So it's really well defined, no indeterminacy, just the holomorphic maps from X to P1. So we should really study that phenomena carefully. Holomorphic maps from X to P1. It's a big breakthrough in mathematics here to forget that that's a function. You should think of it as a map. I think it's a big breakthrough. I think the open mapping theorem is a big breakthrough. The fact that a holomorphic function is a mapping is a big breakthrough. This is, I think, due to Schwarz, and I think it's due to Schwarz in the early 20th century. I mean, not long ago. I think Riemann maybe didn't think that way. Okay, Riemann understood everything, so I'm sure Gauss did not. He talked about conformal mappings, but nowhere did he talk about open mappings. Yeah, it's difficult to say. The language of the time was something else. So anyway, I shouldn't probably conjecture.
Question.
Yeah.
What is the P1 here? What is the Projective space of functions, is it?
No, projective, one-dimensional complex projective space. Here, so let me say it again. Let's look at the top. The idea is, if you take all these local things, then you can write locally that, and it gives you this thing into that's homogeneous coordinates. So that's really in P1 of C.
But f alpha and g alpha are functions, they are not complex numbers. How could it be?
Yeah, no, given a point, f alpha is a number associated with that point, and g alpha is a number.
Okay.
So the pair, let's go through this again. I'm glad you asked. The pair is a vector in C2, right? So that vector in C2 determines a line, one-dimensional subspace. And if you're looking at the ratio, f alpha divided by g alpha, right? That line and that ratio are the same thing, right? So we have a map to P1 of C, or P of C2. That's the map. And the compatibility condition here means is well defined. Okay, it doesn't matter what you choose. Of course, we choose these things to be relatively prime. That means in the case of one-dimensional case, either one or the other is not zero. So that really makes sense. Okay? So it is, and I guarantee you, it is better to think of these things as maps. I guarantee it. Okay? So, and of course, they're just the holomorphic maps to P1. So, I will go back up quickly. So let me talk about a picture of a holomorphic map. So this is a secret picture, but this secret picture you find explicitly in Riemann's papers. So this is exactly the way, actually Riemann understood everything. It's just incredible. So a picture of a holomorphic map. F from one where dimension x equals dimension y equals 1. Okay. So the first thing in this picture is you have an upstairs space and a downstairs space. I always have my downstairs space will look like that. Again, this is it. If you draw a real picture of this, this is perhaps something like this. I don't know how it's like, but this is a schematic picture of a one-dimensional complex manifold. Okay. And now the upstairs, so now if you have a point down here, let's simplify this. Most of my discussion will be completely general, but let's just say here, for simplicity, x and y are compact and connect. And just to make sure you don't get upset about something, and f is non-constant. Let's take that case, and if you understand that case, it's good enough. Okay? That was not, this is the first thing. I come to Germany and I have all these great view of this great German complex analyst, and I give some lecture. I give a lot of lectures around. The first thing these guys ask me about is the map constant or not? I said, you have to be kidding me. Right? The map is non-constant, otherwise I wouldn't be in this room. Right? Come on. Come on, give me a break. So, the map is non-constant. The map is therefore an open mapping, right? Because everything is connected, right? The map is therefore, in this compact case, surjective, because it's a map of, the image is compact and open, so, and everything's connected, so it's surjective. So, this map is surjective. So every point here has pre-image. Otherwise, if this stuff is non-compact, it may not be surjective. So here's the map. It looks like this. It always goes from top to bottom. And of course, the pre-image has some points. The pre-image is discrete because if it had accumulation points, the identity principle says the map is constant. The upstairs manifold is compact, therefore the pre-image is finite. Okay? So the pre-image looks like this. I don't know. Now in life there are good things and bad things. Right? For example, the weather is bad from my point of view. Okay?
Seen worse.
Huh?
I've seen much worse than this.
Yes, that's true. Okay, so we have good points and bad points. So, you know, I think we should be optimistic. Let's look at a good point. So let's call this be good. That means that the map does not ramify over P. That means that at every point here, the map is of maximal rank. So, a mapping has a Jacobian. A Jacobian, if you like, well, the mapping has a differential. Okay. The differential in this case is a 1-by-1 matrix if you write it in a coordinate because it's a holomorphic differential. I mean, you're talking about maps which are complex and linear locally. So, this has a differential which is a mapping from a one-dimensional tangent space to another. And it has a rank. And the rank of that map is either 0 or 1. Okay. Locally speaking, that is whether a number is 0 or 1. This number is, or not 0. This number is a holomorphic number. It varies analytically with the function. Therefore, it only vanishes on a finite set. So, there are only finitely many bad points up there, and so we remove them at first. Look at the good stuff first. That's the lesson you learn. Look at the good stuff first, throw out the bad stuff, and then understand the whole thing by analytic continuation going back to the whole thing. So throw out the bad stuff, understand what happens, and then go back to the whole thing by analytic continuation of the whole thing. So there'll be some bad points over here. That's a bad point maybe here, here, I don't know, here, here, here. Let's say there's so many bad points. And these are all good. That means the mapping has constant rank 1 here. That means it's an open mapping here, which is locally the mapping Z. Because locally every mapping is Z to the K. And so it's a question what K is. And since the Jacobian doesn't vanish, K is 1. So this is in fact Z. In fact, this identifies here a neighborhood of that point with downstairs. We say it is unramified at such points. So if I take a good point where there are no ramifications over that point, that means I take a non-critical point in the sense of Morse theory or the sense of anything, non-critical image value, non-critical value is what one says. Yeah? Then there are no critical points above it, and you can choose it to be a covering map over that point. Okay? Now, here is another point. This point here is a bad point because it has a ramification point over it. That means there is, in this case I chose one picture over it, one point over it ramified. So there may be other good points here. I mean, maybe there's only one bad ramification point here. So, who knows? I don't know. Maybe over here it's still good, and so on. Let's say something like this. Now let us say, now we go to this bad point. We go to this ramification point. I go there and look at it with a microscope. Okay, I just went there. So, locally, I told you this morning, you know it very well, locally a map is Z to the K. that means there's a number k associated with that map at that point. K, z to the k, has 1 0 and is nearby k to 1. Right? So let's say this is nearby, I don't care, 2 to 1. Well, that's how it looks. So what happens here, let's just have fun here and say that in that fiber here, there are 3 points. Yeah. And this ramification number here is 2. So this, I don't know whether the ramification is 2 or 1. Let's just leave the picture right now. So there are 4 points, and here this ramifies here. You leave the point a little bit, go into genericity. I told you this morning, please go to genericity. You leave this point a little bit, you go up here, and it's again 4 to 1. You see, you leave a point here a little tiny bit. Let's leave it a little bit. And we go here nearby. We have to go to a small neighborhood nearby, otherwise we get hooked with this ramification. And this thing is then again 4 to 1. Here it is 4 to 1. In a big neighborhood of this good point, we don't know where the bad points are. Well, what happens here is that you're on this good stuff and you move here toward this bad point. So we're moving toward this bad point from the good point. And in between, there are no bad points. If you don't hit ramification, you could continue on. And what's going to happen is you're going to do this, and then finally you're going to come to a ramification point. So what's going to happen is this. Okay? So I want to mention here, just for fun, you have a number 1 here because it's 1 to 1. You have a number 1 here because it's 1 to 1. You have a number 1 here because it's 1 to 1. Number 1 here is 1 to 1. You have the number 1 here, it's 1 to 1. You have number 2 here, it's 2 to 1. You have the number 1 here. By deep thought, you notice that 1 plus 1 plus 1 is 4. Yes, it's a 4 to 1 covering map generically. If you count with multiplicity, 1 plus 2 plus 1 is also 4. You go over here, maybe what could happen is a tragedy here. You could have some awful thing happen to you here. I don't know how this could look like this, but you could very well have that happen. If you go over here and this ramification is 4 to 1, but it is an obvious fact that if you count the number of points in each fiber with multiplicity, it is constant. Right? You can just check it. So there is a number associated to this mapping, which is the number 4. The degree of this mapping is 4, and it is a very, very strong statement. The degree of the mapping is a concept of differential calculus. This degree of the mapping states that outside of a finite set, which is the image of places where the Jacobian vanishes, which is called the branching set of this mapping, and it's downstairs. The branching set is downstairs. So B equals the bad points. The bad points downstairs. This is what is called the branching set of this mapping, and I always get confused between the branching set and the ramification set, which is upstairs. So the ramification set are these points upstairs, where the Jacobian vanishes. So rank f equals the derivative equals 0, where the Jacobian really vanishes in local coordinates, is called the ramification set upstairs, where the map ramifies. And the way to remember that is B, the points downstairs, B is for base. That's the only way I can remember it. Okay? So the base point set is downstairs. So now, what it states is if you remove, so if this map is called F, and you look at the mapping X from F inverse of the branching set to Y minus the branching set is a D to 1 holomorphic covering mapping. is not necessarily Galois.
What
That-
is
Hmm?
what is D? D's a degree.
I'm sorry, D, yeah, thank you. So D will be the degree of this, whatever it is. In this case, 4, okay? You just go to a generic point, count. Okay, how many points are in the fiber above it, okay? Okay, so you can check that. That's a fundamental picture that, of course, Riemann understood. By the way, from Riemann's point of view, a Riemann surface is the upstairs space. Okay? And for Riemann, it's very interesting. Riemann, if you ask him what is a function, for him, a function may be multiple valued. And so the function may not be defined, it may be something like this. You see, the value of this function could be the inverse of this function. It has 4 values, generically. Riemann was much more general than we are. His word for honest-to-God function is uniform function. Multiple function could be 4 to 1 or 10 to 1, because he wanted to understand square root, for example. See, he wants to understand algebraic equations, and the equations have of 2 variables, and the equations have solutions which are multi-value. Right? So this is his picture. Every holomorphic mapping is in this sense a cover.
Let's
Yes.
ask another question.
Yeah.
Here you discuss about the ramification points, but I intuitively understand must use the implicit function theorem or rank theorem, but could you please explain more that why, like there are 2 lines intersecting at that point, what does it mean?
I'm sure I use everywhere here the rank theorem. So let me see. In this case, it is so trivial that I almost don't call it the rank theorem. Let me just review what I use here, okay?
Can I please comment on something?
Yeah, you want to comment on the same thing?
Yeah, I was in the course with him. Like, do you remember the theorem that if the derivative is not 0 in one point, the function is ejected there, around
Oh, yeah.
a neighborhood?
Yeah.
So, because it's 0 there, it has to not be injective, so it has to have at least...
Okay,
two
so-
values.
Let's talk about this a little bit, because maybe, you know. So first of all, the Jacobian. And the complex Jacobian is just in local coordinates this. Okay? If you write the real Jacobian down, it will be the absolute value squared of that. Right? But this is I call this the complex. This is a complex linear Jacobian. So it's in this case it's a number. Okay, and this number is either 0 or not 0. And if it's not 0, the mapping is locally f of z equals z. Yeah? What is with you? Mihai, do you have something more?
I just wanted to ask you if, like, in my head, holomorphic between 2 Riemann surfaces means locally holomorphic. That's what it means. Like, you go to the charts,
Yeah.
and it's holomorphic on C. That's what you go.
Yeah, yeah. Very good. I did. Yeah, please make these questions.
Mm.
Yeah.
So you use the definition on C because you didn't give any.
Sure.
Mm.
And that's the point with holomorphic compatibility. It means this definition is well defined.
And holomorphic, how do you define holomorphic? I mean, I was not here in the
That's okay.
beginning, but I mean.
We have a nice review. It's nice.
What does it mean that it's holomorphic in multi-dimension? Does it mean that it's holomorphic in each of the variables?
Yeah, I talked about this morning. So it means that d bar of it is 0 as a function. That means, say the smoothest definition is let f be a smooth complex valued function, smooth, and holomorphic in each of the variables. But Hartog's theorem tells you, with virtually no assumption, just holomorphic in each of the variables separately, and it follows that it's smooth. This is not at all clear because you know there are discontinuous functions which are smooth in all of it. Okay?
It's more powerful because it's about complex numbers than about real numbers.
Yes, absolutely. It's a very, very powerful condition, particularly in higher dimensions, somehow. Yeah, that's very good. All these remarks I appreciate very much. Thank you. So are we okay on this centile?
Mm-hmm.
So this morning, again, I said that locally speaking, after a change of coordinates, every function is z to the k. And that's what I'm using here, that I localize the discussion here. There's a function locally. That's what we just discussed. and it's just simply z to the k there, and in this case it's 2. Over here it's 4. Generically speaking, is 1. Throw out the points where it's bigger than 1, and it's, of course you have to, see here it's 1 and here it's 1, but if you want a covering map, you have to throw all these things out here because of this one ramification. You must throw out, you see what I did, I threw out the pre-image of all the bad points downstairs. And it's now a k to 1. Okay. The statement is a holomorphic mapping from x to y in one variable has the same number of points in every fiber. Okay. Every fiber is finite, and it has the same number of points in every fiber.
Counting multiplicities.
What?
Counting multiplicities.
Counting multiplicity, correct. And of course, you can write down a formula. What you do is you associate each point to multiplicity, and the statement is the sum of these numbers is a constant. And that's then the degree of this method. Okay, so that's the story there. So a rough statement, a corollary. Every m in X has the same number of zeros as poles. Right? Because in that case, you do this, you say, well, the downstairs is P1, upstairs is X, maybe it's 4 to 1 like over there, and maybe here's infinity. So maybe it's has multiplicity 3 here. So it has a pull of order 3 and a pull of order 1 at another point. And maybe over here is 0. And over here, maybe it has, I don't know, pull of order, 0 of order 2 and 0 of order 2. So that says the same thing as 2 plus 2 is the number of zeros, and 3 plus 1 is the number of poles. Okay.
So, how? I mean, isn't 1 over x isn't a meromorphic function on the Riemann sphere?
Yeah, so let's talk about that. So, Mihai's example. If you don't mind, I will take z. Just z. So z is a meromorphic function on P1. Let's check how it is. Well, we take on C0, on U0, M0 equals z, and on U1, M1 equals 1 over zeta. And on the overlap, z equals 1 over zeta, so it's globally defined. So what this says is this function z has a 0 at the origin and a pole at infinity. Okay. 1 over, if you like, I will draw you, this is a biholomorphic map. So here's P1, and here's P1, and here's the base, and this is the function, it's z. It's 1 to 1, biholomorphic, just maps. What's the problem? Is there a problem?
No.
Okay. So any polynomial, let's look at a polynomial. Okay? So you're just not used to this stuff. You take any polynomial z, say it's now let's start it, let's make it monic so that it doesn't. So a polynomial of degree d, ad, d minus 1, d, you know, such a polynomial. All right? Now we prove the fundamental theorem of algebra. Fundamental theorem of algebra says that here's P1. and this has ramification and so on, I don't know. But,
So it
This-
does the polar order D at infinity?
huh?
It has the polar order D at infinity?
Yeah. But every value is taken on d times. You see, the fundamental theorem of algebra is proved by the fact that this mapping is surjective. That means every value is taken on. And then by recursion, you prove that it has so many zeros and so on. But by this whole thing here is every value is taken d times. And let's see if Mihai is right about that. Let's check this. I have to put in here a zeta, right? So this is equal to 1 over zeta to the d plus 1 over zeta to the d minus 1, and so on. And I factor this out, 1 over zeta to the d, 1 plus some stuff here. So I'll write what it is. So it's this times a unit, which doesn't vanish. So as you point out, it has a polar order d to infinity. Okay. So you easily check here, using these kind of arguments, that the meromorphic functions field of P1 is the field of rational functions in Z. Right? You just check it. Here's the proof. You can assume that given a rational meromorphic function, it doesn't have a polar to infinity. Then you write down a polynomial with the right number of zeros on its complex number, with the right zeros on the complex plane, the poles on the complex plane, take the quotient, and this will be your function. Because and the point is, you really need the fact that you have the same number of zeros as poles, because then there won't be anything at infinity, right? They cancel out. Right? So, this is this fact, and when that's the first theorem of the course, the function field on the complex number plane is just that. Hope you know that value distribution of non-compact manifolds is highly non-trivial. People who do dynamics know that very well. You see, the stupidest theorem is in the neighborhood of an essential singularity. Yes, you have the big Picard theorem, which says every value is taken on so many times and so on in any neighborhood of an essential singularity. This is a very weak theorem. The big theorem is that measured theoretically, the fibers of this mapping are all the same except for maybe 2, something like this. And then you get into so-called Neverliner theory, which is much, much deeper. So, and this is only one-dimensional stuff, which is not, to me, not very interesting. So higher dimensional stuff is much more interesting because you have the dynamics of the curve, which is really moving. You see, you're talking about images which are curves and how they intersect other curves and so on. That's the deep Neverliner theory in higher dimensions. Okay, but here we are in a very simple situation where everything is compact. Any questions at this point? I think we talked nicely about symptom. You okay at this stage?
Yeah.
Good. Okay. A little bit quick, but this is it's a very beautiful theory. And of course you notice I like it very much.
So this theory is also true in higher dimensional space?
The right version of it is true, but you're going to see right away that immediately there's some delicate points. So I will explain the first delicate point now.
But you don't have discrete zeros in higher dimensions.
That's really the end, and the two functions can their zero set, simultaneous zeros that can be something, like I drew in that picture someplace. Yeah. So I'd like to discuss that. But before I do that, let me just make one more remark in one dimension, which I love very much, so I'll make it. This is really a relevant remark, and it is very beautiful. This was written down by Riemann without proof, and was proved by Horowitz, and so it's called the so-called Riemann-Horowitz formula. I don't know who really proved it completely. Felix Klein certainly understood it. And it's in this context of what I'm now going to call ramified coverings. Okay? So, finite ramified. Riemann-Horowitz formula is this. Well, you need to recall a simplistic definition of the Euler number of X. So still in a one-dimensional case. The simplistic definition of the Euler number is due to Euler. So Euler was optimistic and believed you could triangulate any surface. I doubt that he proved that. It's slightly interesting, particularly for topological surfaces. Anyway.
Can you do that with non-orientable surfaces?
Say it again, please.
Can you do that with non-orientable surfaces?
I don't know. Probably.
I think I heard the theorem, but it is for.
Well, I don't think that's. I don't think that's a problem. What's the point? Is because you always have a 2-to-1 covering, which is orientable, and now we just triangulate upstairs compatible with the covering. Right?
Maybe it just doesn't say whether it works for non-orientable surfaces or not.
Oh,
it works for orientable surfaces.
Well, I know what you're going to say. The formula that I'm going to write down here is for orientable surface. Yeah. So you know the second homology of a non-orientable surface is 0. Usually the second homology or cohomology is 1, and it's generated by the volume form. This is a 2-dimensional surface, so the cohomology is you have the top orientation form. But if it's not orientable, the second cohomology is actually what is it, 0 or Z2? I guess it's even Z. Anyway, I get it. I get nervous, but you're really right about this. You should always watch out for non-orientable stuff. I agree with you. So here everything's orientable because it's complex analytic. Yeah. The change of variables is holomorphic, and that is always the real Jacobian is always positive, right? Because it's the absolute value squared of the holomorphic transformation. Okay. So, but thank you for your remark. So Euler's definition, you know, is with the triangulation. So the topological Euler characteristic of X is let me see in which language we are here. The number of, okay, let me try it. You know, it's vertices minus edges plus faces. So we have the same letters. Of a triangulation, then I guess if you have a triangulation, if Euler had a triangulation, I think he proved that it's well defined. Independent of the triangulation. That's a fantastic fact, right? Okay, and you can check that for our X, which is the surface, that this topological Euler number of X is 2 minus 2G, where G, we'll talk about this in great detail, so I'm just being rough now, is the number of handles to build X as a handle body. in many ways, I mean, this is, you know, right at the beginning. I have to do something to get a definition. Let me just draw the picture of what I'm thinking about here. You may look at something of genus 2 like that, but somehow when I look at it like that, it's hard for me to say that has genus 2.
So this 2 minus 2g is just in one complex dimension, no?
I'm still in one complex dimension.
Okay.
And that's good that you repeat that. Everything there's only one topological invariant in dimension for real dimension 2. If it's oriented. And that's the genus. And the genus you can think of as a number of handles, and it's better to think of as a number of handles. So the way to think about this is you take the sphere, and you take 2 holes in the sphere, and then you attach a handle here, and take 2 other holes here, and attach a handle here. And it's very precise what it means to attach a handle. I mean, there's what we call a collar here, and it gets attached by, this is an annulus, and there's a gluing map on the annulus which defines an equivalence relation. And this is the topological classification of 2 manifolds. And there is this number g, which is the number of panels.
But in the first picture, the g should be 1.
G is 2.
doors.
I don't know, 2 handles, 2 holes. So g is 1 is this.
Yeah, but then this is the number of holes, not the number of handles.
Yeah, it's the number of handles. You can build this surface with these handles. Don't you see that's the same thing? See, okay. I take the handle here, and take the handle here, bring it over here. You see? Okay? This is all blah blah, but I mean, let's hope. For those of you, and you should be familiar with basic topology, and I'm very upset that there's no decent topology discussion at this place, so we should start a discussion. The correct first definition of the Euler number is the alternating sums of the Betti numbers. The Betti numbers are the dimensions of the singular, I would say, the abelianized homology, or the cohomology. So, and this is, you see the Betti number, you see, this is the 0 Betti number, the first Betti number, the second Betti number. These are in the triangulation of this thing is the CW complex. This is how these Betti numbers are computed. So this is really the correct way in modern mathematics to discuss the Euler number. And the Euler characteristic of any object is the alternating sum of its cohomology dimensions. There are all sorts of Euler numbers around life, not just in geometry. Okay. So, okay, that's an Euler number. And now, let's look at a ramified covering. Oh, I erased it. It's too bad. Okay. So let me try to write that 4-to-1 cover again. So here, let's make one like this. Let's just make a simple one. So something like this. And this is x, and this is y. And not just a meromorphic function, something. So surface x, Riemann surface, holomorphic map from Riemann surface to y, ramified covering. Okay. Upstairs you have the ramification points. Downstairs you have the branch point. Okay. Now you take a triangle, let's take a good triangle. Let's do the naive definition. I love it because it's so naive. I love naive things. So this is a triangle. Okay, you see it. I mean, I can't draw it. Okay. Now I lift it. Well, it's a triangle. I want to miss this ramification. I lift it.
What did the student from Congo say?
Huh? What?
What did your student from Congo say?
Yeah, yeah. Yeah. It's true. People don't know me. I had some student who came from Cameroon, and he wasn't very, at first wasn't very abstract in mathematics and so on. And I kept drawing these pictures like this, and he kept telling me, "But professor, The surface doesn't look like that. No, really, really, I mean, yeah. And so, okay, this is a triangle, and these are the lifted triangles. So if you take a downstairs triangle, you lift it and you get 4 upstairs triangles. Now I can take a triangulation downstairs, even at the bad point. I can put a corner at the bad point and take the triangulation outside of it. So nevertheless, even though I have ramification involved in this discussion here, I have 4 triangles above it. It's only the statement that I can take a triangulation downstairs with the corners at the branch points. That is a stupid fact. I mean, you can just, this is visually obvious. You got finite many points, you just have to do this. Okay, so we have the Euler number of x, well, equals, let me just say, equals v tilde plus minus e tilde, v tilde edges, plus f tilde. And Euler number of y equals v tilde minus f e plus f. And now we compute. Okay. Well, f equals f tilde. Right, because, yeah?
Faces up, lift the faces.
Yeah, the faces just go up. And I claim also the edges.
Yeah,
Because
The faces go up.
yeah, the faces.
Sure. The faces go up because I have the same number of triangles downstairs as I have upstairs.
How many degree times?
Aren't they multiplied by 4?
Degree
Wow.
times.
Yeah, yeah. I divided out by the degree of the map. Yeah, thanks. So f tilde is 4 times, okay. 4 times. Yeah, thanks. Well, maybe I should drink something serious. Okay. Okay, and I claim that same statement for the edges. Because only the corners get involved with the ramification, right? So the number of edges goes up. Okay. So that says, I'm going to make a mistake here, the topological Euler characteristic upstairs equals the topological Euler characteristic downstairs times the degree of the mapping. Yeah.
Minus the cardinality.
Minus, I've got to make a correction now, right? And it's minus, the number we call it is the degree of the ramification set. Okay, so let's, minus is right, yeah? Minus the degree of the ramification. And now I have to tell you what is the degree. The degree, when this is 2, is 1. Right, this is, yes? So no ramification means degree 0 ramification. That makes sense actually, right? This is no ramification, this is 1 ramification, this is ramification 3. So this is the degree of the ramification.
So this is sum?
Huh?
It's a sum of.
So, yeah, sum, obviously, yeah, I'm sorry. This is the sum of over all ramification. Okay, so here, let's see what we can get just for fun. I have no idea what these numbers are. Euler characteristic upstairs is 4 times the Euler characteristic downstairs. This is a huge obstruction to mapping. Minus, what's going on here? 1, 2, 3, 5. By the way, is that right?
Yeah.
I think this can't happen. Because, as I pointed out to you, might be non-oriental. No, you see, this thing is an even number. Right, it's 2 minus 2g. This thing's an even number. So this, my example doesn't happen. No, that's interesting, right? It doesn't happen. You see what an obstruction is. You draw these little pictures and most of them don't happen, yeah?
Would it work, could there be a counter example even if the number is even?
Yes, indeed. but that's a very, very, so now, yes indeed, so now you posed a really interesting problem, right? So we have, and this is a problem very close to a problem posed by Grothendieck, which is a problem of, he calls it little pictures or something like this, of which little pictures really happen, and trying to parameterize somehow, given a little picture, what really happens and how it happens. Yeah? And even in dimension 1, it's very interesting. He has a name for this in French, and I'm sorry I've forgotten. You know?
Dessin de fond.
Yeah, oh, because it's about children.
And yeah, the painting of the children. Yeah.
Yeah.
Dessin de fond.
Yeah, so this is a painting of children. Oh, it's beautiful. So,
So there is no function that looks like that. Huh? There is no function that looks like that. For example, from the Riemann sphere to the Riemann sphere.
no, there's no ramified covering. It has nothing to do with homomorphicity. I didn't use homomorphicity here at all, really. It just doesn't happen because the number is, yeah, but this rigidity is very strong. I was actually very lucky to get something that doesn't happen.
Not quite sure again that there doesn't exist such a map.
There does not exist, let me write it. Since this is even, and this is even, and this is odd, even equals even minus odd implies doesn't happen. Yeah. So you see what kind of a nice invariant that stuff is. So this is a beautiful formula. This is called the Riemann-Hurwitz formula. And it took our giants of our past to prove it, although now we understand really what's...
Professor, I have a question. Is there any reason, like any serious reason, for why they multiply there by 2? Why is it 1 minus g?
Yes, Poincare duality. But he asked, why is the number 2 there?
Yeah.
Why is it even? I mean, that's what you're asking.
Yeah, it's always even.
Yeah, let me look at that, explain that to you, okay?
Mm.
I don't know when we started at 3:45, and we should end at 5, so I'm a little bit,
That's fine.
so I will explain that and then we'll stop, okay? So y is this topological thing of x, an even number. That's your question, right? Somehow. And here we really use orientability.
So you can compute that only for orientable surfaces.
Yeah, and you will see why. So maybe this doesn't happen. This does happen for non-oriental. I don't know. It's what Tane's saying. I'm not really sure of this whole business for non-oriental. I should be really careful.
Because otherwise you would consider that the Mobius band has a pole of 1. And you cannot do that.
Right. Well, of course, it's not compact. So the first thing to look at probably is P2R.
Okay.
When you take the sphere and identify opposites, it'd be interesting to check what's going on there. I should know, but
the upper hemisphere, huh?
huh?
The upper hemisphere, or?
Yeah. No, well, no. You had the full sphere, and you just identify opposite things.
Yeah.
No, because you're identifying on the boundary also.
Okay.
So it's not quite the upper hemisphere. It's the upper hemisphere compactified
Yeah, okay.
by real projectors somehow.
Yeah.
It should be much uglier than the upper hemisphere. I mean, it's not very easy to
It's very funny,
it's
right?
the plane with the line of infinity, no?
Yeah. That's the easiest way to think of it, I think. That's what it is, P2R. But you know, I think of that as the real points in P2C. And that's my favorite warning, is to think of these real structures as the real points in complex structures. Even with the real line, and that's the way Riemann thought. The real line is not the real line, it's the real points in C. And a power, you should start thinking that, what is a real power series? What is it? Yeah, it's really a complex power series with a radius of convergence, right? I mean, in C, but restricted to the reals with real coefficients. So I like to think of it that way. Mihai's question was, why is it even? Yeah, my answer is not going to be very good, I think. So the Euler characteristic of X is equal to the alternating dimension of the Betti numbers where BI, it depends on what you like to call it. Since some of you had my course last time, let's call this the dimension of the Durand cohomology. The dimension over R, this is all the real Durand cohomology of Hj at Durand. But it's the same thing as simply the dimension of the singular homology. That's right here, singular homology, cohomology. And in this case, there is no torsion in this theory. So there's something called universal coefficient theorem, which tells you about how to relate cohomology and homology. And so this, in this case, is the dimension. Maybe let's just say this is really a vector of the Z module of this H n minus G of X. Okay, this is okay. So going to real coefficients doesn't matter. Now, so these two numbers are always equal. So the zeroth cohomology and the top cohomology is always equal. We talked about that in our class, right? By integration. So this is just a general fact for orientable manifolds. And in fancy language, this is a general Poincare duality. But you really don't need it in this case because it's just the duality between the top cohomology and the zeroth cohomology. So that, okay? And these two numbers are equal, and since the manifold is one-dimensional, they're one. This number is one because it is the connected component of the manifold. This reflects the manifold being connected. And this number is one then because the manifold is oriented. Okay, so that's the first two here. Okay. So that says this thing is 2 minus the second Betti number. First Betti number. Okay. Now, for those of you who prefer to think in homotopy, I mean, this homology is the first homotopy abelianized, if this is the way you like to think, I don't know. So here we really have all sorts of things going on that we can use. And this is the interesting thing. You might see some involution which maybe maps one curve on the surface to another curve on the surface. So you might see some natural involution going on the curves. And this involution, from my point of view, is complex conjugation. Yeah? So complex conjugation acts here, and therefore this number is...
Can't we just look at the construction of
Who is speaking? Yes, Tane?
Can't we just look at the construction of surfaces of genus G? Like it is 2G, right?
That's right. You will really see it, is what you're
So
saying.
B1 is 2G.
That's right. You will see the curves. And it's, but I wanted to, you're absolutely right, of course. You will see the 2G, but somehow you see some involution on the first Betti group that maps one set of curves to another. I see it somehow that way. But what he's saying is just look at the curves. You can see the 2G curves, right? You see them, right? you see this curve, these are, I don't know whether Riemann, I don't know. Maybe we should even call, I don't know. Anyway, you should have a base point, but I won't have a base point. I'm not worried about base points. Okay? If you don't worry about base points, you see the fundamental group there. Okay? But I think through
The fundamental group and the cohomology are the same.
okay, these are generators of the fundamental group, and there's only one relation. So you will see. So you will see that then the four generators of the homology. That these things generate the homology freely. There's no torsion. Okay. You will see one relation. Okay. We can get into this if you like. Especially if you're interested in billiards, we can talk about this in a serious way. People are interested in hyperbolic billiards, which means that, I'm sorry, maybe you're not, other people aren't interested, but I could tell you something here. There are fundamental results here. If you take a Riemann surface, its universal cover, as you know, is the unit disk. This is a very important theorem. And this is Riemann mapping theorem in some sense in higher variable. And the next remark is the unit disk has the Poincare metric on it, this very famous metric that you know. And it's a unique invariant metric for the transformations of the unit disk. The biholomorphic transformations of the unit disk. Then you ask a naive question, which is highly non-trivial. Does every element of the fundamental group, an element of the fundamental group is an equivalence class of loops, right? Does every equivalence class have a curve of minimal length? And if it, yes, a geodesic. So the answer is yes. And so you say, I'm incredibly happy, I'm just going to forget the fundamental group stuff, I'm just going to use the geodesics. Then you say, where are these things geodesics? Well, the metric on the Riemann surface of genus 2, for example, is the same as the metric on the disk. So you say, well, okay, I look at the geodesics on the disk. Of course, they're periodic because the group action from the universal cover to the Riemann surface stabilizes the picture. So, and these geodesics, of course, perpendicular to the boundary. So, but the fundamental region for this group action looks like this. It's perpendicular to the boundary. Then this is perpendicular to the boundary. Then this is perpendicular to the boundary. Then this is perpendicular to the boundary. I won't get the number right, and I don't care right now because this is just a qualitative statement. But you get then a compact fundamental region for this thing, bounded by pieces of geodesic. By the way, I didn't. My number is always 5. I think 1, 2. No, wait. 1, 2. Oh, 6. Maybe. Anyway, it doesn't matter. Okay. Now, this is these things come in pairs. Riemann called the A geodesics and the B geodesics. In every country in the world, there's the AB. Yes, and the relation is more or less of the type this type. I don't know. I think this is the relation of the AB geodesics. And now the interesting thing, which is interesting to physicists and many people, is to play billiards on this thing. This has to do with a lot of very, very deep properties of the length spectrum of the geodesics, the eigenvalues of the Laplacian, and many deep things about dynamics of this thing. Now the dynamics of this thing is, of course, you don't forget that these things are identified here. This is a fundamental region. So I mean, this thing's going to bounce off of here because then it goes over to here, and then it goes to here, and here, and here, and here. This becomes a very interesting dynamical system on the universal cover, which really is related to the Riemann surface of genus 2. Now, I have friends and colleagues who even take special Riemann surfaces of genus 2, which we will, or genus 4, but they're already in genus 2, there's some beautiful examples, and are interested in the properties of this billiards as related to physical phenomena. It's very fantastic, very fantastic. And I'm telling you, almost nothing has been proved, and maybe nothing can be proved. It's very, very tough stuff. So you see, even though this looks very trivial, the minute you start asking things like this, we get into some very nice questions. So were there any other nice questions? Centel, you okay on this stuff now? I mean, this is just back stuff here.
No, I mean, after we go to the billiards question, I cannot understand.
No, not yet, no, but it is interesting to notice, you know, the first people who talk about billiards is maybe this kind of billiard table, and you talk about a linear, well, you know, you play billiards and it goes in a line, and then it goes over here and then so on. Well, this is non-linear billiards. These are just the lines of the geodesics of the Riemann surface, right? And they bounce around off this fundamental region. They're going around here in the Riemann surface. Yeah. It's very beautiful. And
Doesn't it like, when I see that thing, that picture with a loop, with a...
which one? This one?
The one with genus 2, yeah. Yeah, the thing, it reminds me of physics or of chemistry orbitals for electrons. And is that a question of billiards, how the electrons go?
No.
No.
Definitely not.
Maybe
that. I think you were looking at some kind of S orbital. I mean P, obviously.
No,
It
yeah, that's
actually
P
is a
orbital.
cloud.
Yeah.
It is a cloud. Basically, electron doesn't have a hole inside over there.
Yeah. Oh, okay.
I mean, the cloud occupies everything.
Okay.
what I can only tell you what some of my friends are interested in here. The classical system, what we're talking about here, is this dynamical system. And they're interested in the quantum limit of this system. So what is the quantized version of this? And these kind of things are very much related to what is called the length spectrum of the geodesics. So the question is, how many geodesics do you have of a given length, or less than or equal to a given length? And of course, you see, you have this geodesic, but then you have closed geodesic or something. Then you have another one much longer. It's very possible, right? So you look at the asymptotics of that. So you scale that, and somehow understand what's called the length spectrum. You can understand the relation between those things and the dynamics of this dynamical system. And even that part of it, I mean, I don't understand any physics, but that part of it is also very, very interesting. So we could, if you get interested in this, I could maybe talk about this in halfway seriousness. Maybe we can invite one of my physics friends up here to give a lecture on this stuff. Very interesting. Tay, do you know about this stuff? I mean, you were studying, you worked in
physics.
You were a physicist?
Yeah.
Good. Okay, see you tomorrow at 9:30.